Mechanisms in motion are short revision videos which show you the effect of arrows in organic chemistry mechanisms. As the format is a quiz, you will be presented with multiple options for how the mechanisms will occur. Based on your choice, move ahead to the timestamp and you will see how your choice affects the reaction. If you are correct, you will move on to the next step in the mechanism. If you choose the incorrect or less likely answer, the reason for this will be explained and then you'll be given the correct answer. Aldol condensation is a useful reaction to form direct carbon-carbon bonds. The reaction occurs between an enol or enolate ion and a beta-hydroxyaldehyde or a beta-hydroxy ketone group. When acid catalyzed, an enol molecule is formed, and with base, the enolate molecule is formed. The first step in this reaction is deprotonation using the base LDA. LDA is very sterically hindered, meaning it will preferentially deprotonate less sterically hindered acidic hydrogens. Here, the LDA molecule can either deprotonate at position A or position B. For deprotonation at position A, the aldehyde would form a ketene. A ketene occurs when a carbon is bound to two double bonds. While this can occur, this is not a very stable molecule and will not occur in an appreciable amount for this reaction. Deprotonation at position B results in the formation of the enolate ion, a molecule composed of a double bond and an oxygen anion. This structure has resonance stabilization. This stabilization also causes the alpha hydrogen to be more acidic, making it easier to deprotonate than the hydrogen of the carbonyl. This is the correct first step. The next step in this reaction is either the nucleophilic attack of the carbonyl of the benzaldehyde or the reformation of the carbonyl of the enolate by attacking with the alpha carbon, or by the oxygen anion. Attacking with the oxygen anion at carbonyl would result in a tetrahedral intermediate. To stabilize this intermediate, you would need to reform the carbonyl in the next step. In doing this, you would need to kick out either a hydrogen, benzene ring, or oxygen with a negative charge. By kicking out the hydrogen or the benzene ring, you are forming unstable intermediates. Therefore, you would kick out the oxygen anion. However, this would undo the step that you just did. This is not the correct answer. Attack by the alpha carbon of the enolate is the correct answer for this step. By reforming the carbonyl and attacking with the alpha carbon, you form a direct carbon-carbon bond. This would result in the benzaldehyde carbonyl breaking to form a tetrahedral intermediate. As kicking out a carbon anion, hydrogen anion, or benzene anion are all unstable options, you cannot reform the carbonyl. The oxygen anion will then be protonated by the protonated LDA in solution, resulting in the formation of an alcohol. This gives you the aldol product. If no acids or bases are added to solution at this point, the aldol product formed is stable. However, the next step in this reaction is adding acid to solution. While both groups will be protonated by the acid, only one of them will lead to the formation of an enol. Which group is needed to be protonated to form the enol? Position A or position B? Protonation at position B forms a positive charge on the alcohol moiety. This group is a good leaving group. However, by kicking out a water molecule, you are not able to form an enol. Protonation at position A results in acid-catalyzed ketone tautomerism, allowing for the formation of the enol. After protonation of position A, the alpha hydrogen can be deprotonated by the conjugate base in solution, resulting in the enol formation. The next step in the reaction is the reformation of the carbonyl by elimination of either benzene or water. By eliminating benzene, you will form a negative charge on the benzene molecule. This negative charge causes the molecule to have 7 valence electrons, breaking aromaticity. This is highly unfavorable and therefore is not the next step in the reaction. The elimination of water is favorable, as water is a stable molecule on its own. Similarly, the final product is stabilized by the formation of a conjugated system. To form the final product of this reaction, the oxygen of the carbonyl needs to be deprotonated, reforming the acid catalyst. This slide shows the overall reaction scheme. This slide shows the overall reaction mechanism with curly arrows as you would draw in an exam. Thanks for watching the video. If you found it helpful, please leave us a like or a comment, and subscribe if you'd like to see future videos of mechanisms in motion.